Good afternoon, everybody, and welcome to this afternoon's session. This is the post-lunch session, so please, if you do feel energy levels are low, feel free to grab a cup of coffee. There's lots of it outside. So this afternoon session, we're going to deal with integrated pest management. A very fitting topic, considering the discussions that we had earlier today on sustainability as well as stewardship and compliance. So we have an excellent lineup of speakers this afternoon. And so, without wasting too much time, I'd like to introduce our first speaker, Mr. Andrew Bennett, who's the General Manager of the South African Bioproducts Organization. This is a pre-recorded presentation, so please, note your questions, jot them down. And for our online participants as well, feel free to post those questions on the chat. And so I think we should be having that pre-recorded presentation coming online right now.
Good morning, everybody. My name is Andrew Bennett, and I'm currently the General Manager of the African Bioproducts Organization. I'd like to thank CropLife for inviting me to speak on the principles of integrated pest management, or IPM. So IPM has a very wide, so this is actually going to be a rather broad coverage of that. I would like to cover the brief history of integrated pest management, or broad history of integrated pest management. We'll dive into some of the principles and strategies, and then look at the pest management tactics that are available. And once we've covered all that, we'll see how it all fits together. And then I'd like to conclude by looking at what comes after integrated pest management. So integrated pest management is one of the most robust constructs to have emerged from the agricultural sciences. And the abbreviation IPM doesn't even need an explanation today. It's a household term. The term integrated control was first ascribed to Mitchell-Bakker and Bacon way back in 1952. And a series of studies of walnut pests, they stressed the importance of consider the entire entomological picture in developing a treatment for any particular pest. IPM to the fore when an over-reliance on synthetic organophosphate and carbamate insecticides started leading to resistance and environmental contamination. And the failures of these new synthetic insecticides led to a resurgence in the work of biocontrol researchers, particularly at the University of California, but also here in South Africa as well. There was a desire to reconcile the use of insecticides with biocontrol options and to the concept of pest management rather than complete pest control or extermination. On top of all of this, the publication of a book called The Silent Spring by Rachel Carson accelerated the acceptance of the integrated management concept. Look on the left-hand side of the slide, we can see that basically prior to World War II, there were no synthetic pesticides, and the only way one could attempt to control pests was using biological approaches. Following World War II and the advent of synthetic pesticides, this whole concept of being able to completely control a pest came to the fore. And the real aim here, and scientists felt that these pesticides were so effective that one would really be able to exterminate the pest. Now, in agricultural fields, that was also the thought, one would be able to achieve 100% control, but also in the medical fields, in controlling diseases that were carried by insects, particularly flies, the idea was one would be able to terminate these vectors and thereby control the diseases that were apparent. Unfortunately, most of these pesticides led to resistance, and that's where the biological approach started then coming into the picture. And this concept of integrated control, of using more than one approach, using a biological approach together with a synthetic pesticide, led to this sort of concept of integrated control. The emphasis here was still on control and extermination, though. And this was like the late 50s, early 60s. And continued use of pesticides led to continued development of resistance. So the idea then started coming to the fore, also, around the 1970s, that one needed to rather manage pest populations. It wasn't necessary to exterminate them completely. And this led to the concept of an economic or some kind of threshold level below which you wanted to manage your pest population to. The idea of a threshold was that, and particularly an economic threshold, was that the cost of the control measure that you took had to be less than the benefit that it delivered. If the cost was more than the benefit that it delivered, then there wasn't much point in applying that control measure. So all of this together led to the ultimate integrated pest management concept, which was very popular from the 80s onwards, and is still, as I say, one of the pillars of how we manage and control productivity in agricultural fields today. And this integrated pest management really relies on managing pests below an economic threshold, relying on understanding the pest's ecology, and also aiming to reduce the environmental impact of the control measures that we use. So in general, by the end of the 1960s, there was basically agreement. Integration meant the highest use of multiple methods to control pests, as well as looking at the impact of multiple pests. Pests were considered any organism detrimental to humans, including invertebrate and vertebrate animals, pathogens, and weeds. IPM was considered to be a multidisciplinary endeavor, so many different scientific branches conducted 2 IPM programs. The idea of management rather than of control kind of refers to a set of decision rules based on ecological and economic principles and considerations. And then the backbone for this whole management concept was the reliance on the concept of an economic injury level or an economic threat to which you wanted to manage pest population. A good overall definition of IPM, which emerged in the 70s, was that IPM is the intelligent selection and use of pest control actions that would ensure favorable economic, ecological, and sociological consequences. This whole idea of IPM was based on a bunch of principles and strategies. And amongst those principles was the appropriate selection of a pest control method used either singly or in combination to manage this pest level below a set threshold, which had to be determined. There had to be economic benefits to both growers and to society and to the environment. And often these environmental benefits were not that the environment was enhanced in any way, but that it was more about reducing the impact of agriculture and in particular the use of pesticides. And so reducing that impact was taken to be a benefit to the environment. There needed to be decision rules that guide selection of control action that one ultimately chose. And there was this idea of considering the impacts of multiple pests. This really means if you control one pest, what impact does that have on perhaps a secondary pest that now emerges as the major pest? And also in this bucket, when later the of control measures on natural enemies of the pests is also required to be taken into consideration. In order to IPM strategy or program together, a number of strategies or concepts were also very central to this, and these had not been there in the past when one just applied insecticide. So one of these, and perhaps the most important, is the idea of monitoring the pests and the natural enemies in an agricultural production area. It's very important to know what levels those pest populations are reaching, and together with that, the idea of a threshold level aimed at reducing the use of pesticides. So these thresholds could either be based on an economic threshold level. As I mentioned earlier, this is where one would evaluate the cost of applying a control measure versus the benefit that that cost delivered. And the other kind of concept around this was an injury level. How much injury could the crop take without becoming non-profitable for the grower? The other strategy was the integration of many pest management tactics, and all of these tactics can really be lumped into two big groups: the sort of preventative or prophylactic practices, and then the curative practices, and we'll go into that in a few moments. And then part of all of this as well is that you need to apply a continuous feedback throughout the season. So once you've basically applied a control measure, one needs to be able to monitor the pests again and determine whether that control measure had a positive effect or not. If it didn't, obviously you need to try something else. And if it did, then there was no need to continue with the control process. So this idea of feedback and continuous monitoring throughout the season was a very important part of IPM. If we look at these that I've called tactics, the various control measures, and we put them into two different buckets. Interestingly, the preventative or prophylactic measures that should be used routinely and should not be based on whether a pest is present or not in the field, or what the level of that pest population is. So these measures include things like cultural control or management, such as rotation and intercropping, in other words, providing changing habitats for pest populations, manipulating the planting or harvest dates to avoid the peak populations of known pests, and then some new ideas, solarization, which is the heating up of the soil using plastic or other means and the sun to deliver heat to that environment and thereby control or kill various pathogens, and things like phytosanitation as well, which is the removal of crop residues after the seed, so as not to provide a habitat for either insects or other pathogens. Then quarantining and regulatory management, also very important, particularly crops where the plants are very susceptible to diseases, in particular viral diseases. So I think of something like tobacco, where you make sure your hands and boots are clean before you go to a tobacco field, because the chances that you're carrying a virus with you is very high. Probably the biggest pillar around this whole group of measures is plant resistance and breeding for host plant resistance in crops. And where we see that crops have a good value, normally a very intensive breeding effort behind that. And the breeding effort is not only related to developing higher yields, but it's also aimed at delivering resistance to particular pathogens, often diseases, but sometimes insects and so on as well. And in turn, this obviously makes those varieties more valuable and allows the breeding or seed companies to charge more. Again, ultimately, the aim is to reduce the effect of a pest to such an extent that using this method is more economic than not using it. And then perhaps a particular instance of host plant resistance is the use of biotechnology to impart particular resistance characteristics to a crop. And we've seen the development over the past 20 years or so of herbicide resistance and particular resistant traits as well. So all of these preventative measures should be used routinely, irrespective of whether the pest is there or not. Once we do have a problem and you need to apply a curative measure, these should really only be used when the pests exceed this set economic injury level. These curative measures are also manifold. Many of them are physical or mechanical. For example, using tillage to expose pest larvae out of the soil so that they die and reduce the population for the coming season, or such things as mechanical weed control as well. Some of the more interesting ones include the inundative release of biocontrol agents. And in South Africa, we have a number of organizations that actually breed up parasites and parasitoids for release in orchards and greenhouses to control pests. So that's a nice one to see as well. But by far the reliance is still on chemical applications, both for insect control, the control of diseases, as well as weed control. And an important aspect of the application of chemicals more recently has been the development of the idea of being able to manage resistance. So within CropLife, as you well know, there are various working groups, global working groups, that look particularly at how to manage resistance and prevent it from developing in various crops and to various insects. So moving in, how do we put all of this together into an IPM program? And the place to start is really with the preventive measures. As we said earlier, you really need to use these irrespective of the level of the pest population, whether it's there or not. But together with the preventative measures, there should be some activity to monitor pest populations. So pest surveillance measures are really important, and these can be put down in various ways. So scouting, where you actually sample a number of in the field and check each plant for the presence of the pest, is a pretty basic way of doing it. Some of the more usages of modern technology include pest modeling, where you put a whole lot of it into a computer program, and the program predicts when the pest is likely to be at a damaging level, and then this tells you when you can go and apply a control measure. Similarly, we use pheromones to attract individuals to a trap, and the changes in those number of trap captures gives you an indication of the level of the pest in the field. Even more modern technology in this sort of bucket is the use of satellite and drone monitoring to take, in many cases, infrared pictures of a crop field and to determine the areas of that crop field or orchard where the crop plants are under stress. And then this leads you to that area to see if that stress has been caused by a particular pest or not. So the preventative measures and the pest surveillance measures come together in the threshold. And this threshold is really the critical success factor around any IPM program. You need to have a way of making a decision as to whether you need to apply some level of control or not. Unfortunately, these thresholds are really difficult to determine. They require a lot of research. And even once you've determined a good threshold, this changes from season to season, particularly if it's based on economies, profit. So just the mere increase or reduction in the price of the commodity you're producing, i.e., for example, the maize price goes up, that would change the economic threshold. Or if the maize price came, it would change the economic threshold. So, as I say, this threshold is difficult to determine. Once you have determined it, it's subject to change from season to season. And this is probably the place where we fall down a little bit when we implement true integrated pest management. Anyway, out of all that, you get to a point to make a decision. You need to apply some curative measure or not, and then those curative measures come into action, and you choose the most suitable way of doing that. These days, as I say, we still rely heavily on chemical applications, but because we're making a decision based on a threshold, we do actually reduce the number of chemical applications that are required. Even newer technologies these days coming out of the, let's say, machinery side of agriculture is really interesting, where camera technology and artificial intelligence is used to actually recognize a weed and then spray that weed. So one's not covering or broadcast spraying the whole field anymore. I think this is an exciting new addition to this whole IPM process. As I said, you still need that feedback loop back to your surveillance measures. So once you've applied your curative measure, you need to keep monitoring to see it's had a positive effect and reduced the population below the threshold level. If it hasn't, then obviously you need to choose another measure and apply that. So that's really how IPM fits together. But what comes after IPM? As we've said earlier, it's been around basically since the Second World War, some 60 or 70 years. And although it's recognized as one of the most robust constructs, although it's recognized as one of the most robust constructs to have emerged from the agricultural sciences, it does still rely heavily on the use of synthetic pesticides and a kind of curative approach. Since the early 2000s, the harmful effects of pesticides on human health have been assessed and continue to be assessed and continue to be more and more in the spotlight. And rightly or wrongly, these have become major concerns. So today, the issues of ecological sustainability of agro-ecosystems and respect for health are as important, maybe even more important, than the sort of classic issues associated with sustainable development. If we have a look at the number of publications, scientific publications that have come out, in the center there, the blue shows those related pest management, and they reached a peak in the early 90s and have since been declining. And the only other real field that is generating a lot of interest is that around or associated with agroecology. So one of the new concepts that has come out is this idea of agroecological crop protection, or ACP. And this is a concept where the biological and agronomic components of ecology are superimposed on those of the social ecology. And it's really a concept of crop protection based on whole cropping systems and the combination of those cropping systems and how they put together to improve the sustainability of the overall agro-ecosystem. So where IPM is really maybe crop and season focused, if I can put it that way, the idea of ACP is to have multiple crops and how they interact together to reduce the impact on the ecology. So ACP aims to promote the ecological health of whole agro-ecosystems by optimizing the interaction between living communities, both below and above the ground, and combinations of cropping systems. It's built on two pillars, namely biodiversity and soil health, in order to make agro-ecosystems less susceptible to stresses. And in this concept, priority to preventative measures, both in space and time, as opposed to curative measures. So the more preventative measures can bring in to your pest control operation and have these preventative measures applied to multiple sequential crops on that field, the more that this agro-ecosystem framework can work towards reducing these impacts and improving health and the sustainability of these agrosystems. So that brings me to the end of my presentation. Thank you very much for your time. I hope you found it interesting, and I look forward to any questions. Thank you.
Okay, thank you, Andrew, for that insightful presentation on the history and the fundamentals of integrated pest management. I think we'd like to just see if there's any questions coming from the folks in the audience or in the auditorium for Andrew. Okay, if not, I'll just abuse my privilege that I have on the podium and maybe just pose one question to you, Andrew. You referenced that, IPM is intelligent selection and use of pest control actions. It's one thing to preach the principles of IPM. I'd just like to know from you, are our farmers adequately equipped and empowered to make those decisions on the farm? Because essentially that is where IPM is implemented.
Yeah, that's a really good question and a tough one to answer.
Apologies.
No, I think, sure, I guess it's my opinion at the end of the day. I don't think that farmers are all that well equipped, I have to be honest. And I think they rely heavily on let's say, the suppliers of pesticides to assist them in making choices. But, there's always a spread across the population of farmers. So the sort of top-end farmers are probably doing a lot of stuff, and certainly in high-value crops like orchards and so on, I'm sure they're pretty much on top of it. Yeah. However, I don't know that they actually spend a bunch of time sort of thinking out this IPM program and how it's all going to fit together, and they really do rely on advisors to a large extent, yeah.
Okay, so you're saying there's definitely room for improvement on that front?
Yeah, my opinion.
Okay, excellent. Okay, last chance for any questions from our audience. Okay, there's one question.
Andrew, Almay represented Global Gap earlier. To what degree do you see Global Gap helping growers to be compliant to IPM principles and to apply?
Yeah, I think that will be really, I think that will be really down to the choice of what curative measures are available and which have been registered and so on. So there will definitely be pressure on chemical companies, for want of a better word, chemical producers, to deliver and make available products that are maybe less impactful and that meet the requirements of Global Gap and Euro Gap. And that would drive the farmers to really consider those, let's say, curative measures in their IPM programs. Yeah. So, yeah, absolutely, I think we're already seeing stuff like that. If you take the old organophosphates and so on that have been banned, they're not available anymore. So that is driving that program in that kind of direction, yeah.
Okay.
Thank you.
Thank you for that, Andrew. I think we will let you off the hook for now.
Cool. Thank you. Yeah, and I don't know what I sounded like up there, but I don't normally talk like that.
Okay, well noted. Thanks, Andrew. Okay, so we're moving on to our next group of presentations, and these will be from the Resistance Action Committees. So I'd like to introduce just Roleen from the IRAC. She's the chairperson for the IRAC. Cullen from the HRAC, and then as well as Adri Anthonissen from the Frac. And so the next three presentations will follow one after the other, and they will essentially be giving us some updates on the topical issues that are being discussed in those committees. So if we could just have those online presentations come up.
Hello, ladies and gentlemen. My name is Roleen, and I'll be giving you some feedback on the key focus areas of IRAC South Africa. So with the current audience, I don't think IRAC needs a lot of introduction. I'll just say that it stands for Insecticide Resistance Action Committee. And the role of IRAC is to prolong the effectiveness of mostly insecticides by implementing resistance management principles. So the key focus areas of IRAC South Africa at the moment can be grouped in 5 broad categories, namely Lepidopteran pests, sucking pests, group-specific resistance management, referring to the mode of action group of the insecticide, nematodes, and improved resistance awareness and media coverage. So the first pest that we're looking at is the fall armyworm. So the fall armyworm was introduced into South Africa around 2016, and as soon as it was introduced, a call for emergency registrations were circulated by the registrar, whereafter numerous new chemicals were registered for its control. The pest is known to be difficult to control and notorious for resistance development. So IRAC immediately composed the Integrated Pest Management and Resistance Management Information Document to inform farmers and agents and anyone interested in fall armyworm and guidelines on resistance management using the newly registered chemicals. So in addition to that, Northwest University, under the leadership of Prof. Hannelian du Plessis, also known as Prof. Takis, in collaboration with the Maize Trust, did resistance studies with the fall armyworm. They tested the fall armyworm susceptibility to some of the chemicals when it entered the country, and then again more recently, I think it was last year, to check if resistance has increased since the pest entered the country. And shockingly, it has for several of the chemicals increased, with resistance confirmed to beta-cypermethrin, indoxacarb, and methamyl. And methamyl actually increased by 7.3 times the LC80 value, meaning that the concentration to control the pest increased significantly since the baseline studies were conducted. So this is just to show you the methods that were used to do these studies. So all of the resistance testing is done according to IRAC International testing methods. And these methods are pest and chemical specific and freely available on the IRAC website. The second pest that we looked at recently is the potato tuber moth. So bad agricultural practices in the potato production regions resulted in difficulty in controlling the pest, and consequently IRAC, together with Potato South Africa and CropLife, compiled information documents with just some information regarding the pest and bad agricultural practices, as well as the insecticides that's registered and how they work, and then resistance management in general to control the pest. Were published via CropLife in the CropLife Circular and also in the CHIPS magazine. And further, we're also planning on having a road show across the main production areas to just take all of this information to the farmers and agents where it's needed most. One of the other things that IRAC looked at is Nematocite labeling. So IRAC International published new Nematocite classifications. So IRAC decided to compile a document that's applicable to local pest species. This was done in collaboration with a few of our local nematode specialists. So the document contains a bit of information on local nematodes and the chemicals that are registered to use against these pests, and also then guidelines on how to update your nematicides according to the new classification scheme. At the moment, this is not yet being implemented though, so we're just waiting approval from the registrar for implementation so that we can change the mode of action groups without having to submit full label extension applications. So this is just an example of what the new nematicide classification looks like. So on the left-hand side, you can see the mode of action groups that starts with the N. That is the nematicide classification. And then on the right-hand side, you have the IRAC or Frac mode of action group, seeing as most of the nematicides are also used as insecticides or fungicides. So the classification that you would have on your label would then be dependent on the claims that you have on the label. So another pest that IRAC looked into is the tobacco whitefly. So tobacco growers struggled severely to control the pest on tobacco, especially as they had a limited amount of chemicals that were registered to control the pest, with 2 of the chemicals not being used anymore because of market restrictions, which left tobacco growers with only 1 chemical that they could use throughout the season, which obviously didn't work well in terms of resistance management, and it also only resulted in suppression of the pest. So emergency registrations were done for chemicals to control tobacco whitefly on tobacco, and IRAC decided to compile an information document and resistance guidelines to use these new chemicals in the spray program so as to prolong the effectiveness of these chemicals for this use. So the document has not yet been finalized. It's mostly done, but it will be finalized soon and circulated to everyone. This is just an example of the spray program in the information document incorporating the newly registered chemicals that can be used to control tobacco whitefly. The Russian wheat aphid used to be controlled by resistance breeding of wheat cultivars. So most of the cultivars were resistant to Russian wheat aphid. However, due to the development of new biotypes of the insect, this is no longer proven to be effective. Consequently, farmers are more dependent on the use of chemicals, and only 2 IRAC groups are registered for the control of this pest on wheat, and there seems to be some problems with controlling the pest with these chemicals. So the ARC, under the leadership of Astrid, is looking into susceptibility studies to determine whether there's any resistance development of any of these chemicals. IRAC is also looking into product-specific resistance management, and the current example is for Group 6 mode of action insecticides. This imamectin benzoate and abamectin are both Group 6 chemicals. However, they're used to control very different pests. Imamectin benzoate is mostly used for the control of lepidopteran pests, whereas abamectin is used for the control of thrips and mites. So resistance management of these products in a spray program might not be as obvious. So consequently, IRAC drafted a resistance statement to be included on all of the labels of the products containing imamectin, benzoate, or abamectin, just to create awareness. This has not yet been implemented. However, the resistance statement has been circulated to all of the registration holders, and then hopefully soon we can send it to the registrar for approval. A few other things that IRAC has done or is looking into doing in the near future. Firstly, the Emerging Pest meeting was established to discuss insect problems that are not directly related to resistance. So during the IRAC meetings, a lot of problems of insect-related issues were discussed. However, that didn't really fit within the IRAC meeting, but we felt like it was still needed to have a platform to discuss these issues. So the new and emerging pest meeting takes place directly after the IRAC meeting, where any insect-related problems can be discussed. Future projects that IRAC is looking at is investigating suspected resistance of thrips to some of the registered chemicals, as well as tomato leaf miner, and then just in general to increase awareness and media coverage on resistance management. So all of the resources that I referred to and that I've shown you on this presentation can be downloaded from the IRAC website, and you're also more than welcome to contact me and I can send it to you, or any of my colleagues, Roleen van Sale or Tia, and you can also report any resistance to any one of us so that we can look into it and investigate it. Okay, with that, I want to say thank you so much for listening, and also a big thank you to all of the participants in the IRAC meeting, without which this could not have been possible. Please feel free to ask any questions. Thank you so much.
Okay, good afternoon. My name is Cullen and I'm the chairman of the Herbicide Resistance Action Committee of South Africa. HRAC South Africa is an active committee with more than 50 members that meet biannually to discuss all things pertaining to herbicide resistance in South Africa. Today, I'll be giving a high-level overview of the key focus areas of the Herbicide Resistance Action Committee in South Africa. HRAC South Africa is a regional HRAC that forms part of HRAC Global. HRAC Global is an international body which was founded by the agrochemical industry with the main aim of protecting crop quality as well as yields worldwide throughout the continued support of all efforts in the fight against herbicide-resistant weeds. HRAC South Africa, being members of HRAC Global, sit on all of the meetings whereby we can gain insights on what's happening all across the world as far as herbicide resistance is concerned. This also opens up a wide network of experts to assist with regional resistance issues. Feedback is then given at the biannual HRAC SA meetings. The main objective of the Herbicide Resistance Action Committee in South Africa is to maintain the effectiveness and the sustainability of herbicides by coordinating and supporting research, education, and communications to prevent and/or delay the onset of weed resistance. This then includes a major focus on communication with those that influence farmer decisions and behaviors, including weed science academics, consultants, agrochemical industry representatives, as well as crop advisors. While some of the information provided by HRAC may be useful to farmers directly, the primary effort is to assist those that spend most of their time working directly with the farmers. In 2020, a new herbicide mode of action classification system was developed and implemented from global HRAC. So the first question is, why was the herbicide mechanism of action classification changed? The previous revision of the Herbicide Resistance Action Committee mode of action classification was last performed in 2010. This update was necessary to capture new commercialized active ingredients as well as to reflect the current state of knowledge for mode of action and chemical family classification, which ultimately creates a harmonized system that is more globally relevant. This update ensures stakeholders have the latest information on mode of action so that they can develop effective herbicide rotation as well as mixing strategies to manage the development of resistance. So what has changed in the new classification system? With the update and revision, HRAC will transition from legacy alphabetical to numerical mode of action codes. Other important changes include the addition of 5 new or reclassified mode of actions, the rationalization of chemical family names, as well as the addition of 15 new active ingredients. Who proposed the changes? HRAC appointed a working group of herbicide technical experts in herbicide chemistry, weed biology, plant physiology, as well as biochemistry from CropLife international member companies to prepare the update. Additionally, input was incorporated from regional HRAC organizations as well as the weed science societies such as the Weed Science Society of America to ensure global consensus going forward. So why the change from letters to numbers in the new classification? HRAC believes that a numerical coding system is more globally relevant and sustainable compared to an alphabetic code based on English or Latin letters. Another concern about the English alphabet is that there are only 26 letters, and today there are 26 recognized mechanisms of action. Over the next 10 years, we anticipate up to 4 new modes of action to be commercialized, which will then exceed the 26-letter maximum. So when will these changes take place? Countries currently using the legacy system will require a long transition period, including education and communication before a change to numbers can officially be implemented. During this period, HRAC will continue to support the legacy alphabetic codes. However, we hope to fully implement these codes onto our labels by the end of 2023. With these amendments, the mechanism of action classification poster also needed updating, hence the development of a new poster in 2020. The new 2020 poster is seen on the right-hand side of the slide, next to the old poster as developed in 2010 with the previous revision of the mechanism of action classification. Following these amendments, HRAC South Africa then compiled a new mechanism of action poster detailing the alphanumerical mechanism of action group codes alongside their old legacy letter counterparts as a comparative tool to use locally. HRAC South Africa has finalized the e-poster in collaboration with CropLife South Africa, which is now available on the CropLife South Africa website for further dissemination to all parties involved. A key focus for HRAC South Africa will be to identify problem or at-risk weeds and compile resistance guidelines to educate the end user on best practice to manage resistance development. Weed species such as Coniza species, Lolium, Plantago Lanciolata, and Comolana bengalensis have been preemptively identified as key candidates going forward, with the Coniza pamphlet being in its final stages of development. Part of the forum's mandate is to preserve the sustainability of herbicide chemistries by identifying potential cases of resistance in weeds. Once a weed is identified, HRAC compiles weed resistance guidelines specific to the weed in question. One of the weeds which we have focused on was Coniza species, and are in the final stages of the Coniza pamphlet, which will contain resistance guidelines for best practice. During 2021, the next weed that was widely reported as being extremely problematic was Plantago Lanciolata, particularly in the winter rainfall areas of South Africa. As a result of this, during the second HRAC South Africa meeting held in September of 2021, researchers and industry experts gave a presentation on the background of the weed, as well as additional data from work done on glyphosate and paraquat resistance in Plantago Lanciolata biotypes. In February or March of 2018, Palmer amaranth, or Amaranthus palmeri, was positively identified on a farm in the Douglas district. This was the first time that the weed was identified in South Africa, which raised serious concern. Following the positive identification by a well-respected weed scientist in South Africa, HRAC South Africa, in partnership with CropLife South Africa, jumped into action, as can be seen in the tables depicting what actions were performed by the committee, as well as when they were performed. The approach that HRAC South Africa followed in dealing with this noxious weed species was a three-pronged approach, namely, to initiate research on the weed, to limit the spread of the weed, as well as to disseminate information about the weed to all sectors so as to raise awareness as widely and as quickly as possible. Research efforts was initiated and aimed to understand the weed as well as to determine whether it showed any signs of herbicide resistance. Between March and September, seed was collected and the first set of glasshouse herbicide resistance screening trials commenced, with the results being shared in October 2018 during the HRAC SA meeting. Following these results, scouting by specialists started to determine how widespread the weed occurred and ultimately how big of a problem it currently is. This is an ongoing process, and thus far the weed has unfortunately been positively identified in Douglas, Howick, along the Limpopo River, as well as more recently in Potchefstroom. The second major focus was then to limit the spread of Palmer amaranth. In May 2018, a meeting was held with various stakeholders, including DAF or DALOD, the DEA or DEA, SAMBI, Grain SA, and HRAC South Africa to inform them of the current situation around Palmer amaranth. In September of 2018, a letter was sent to DAF and DEA again informing them of the weed's presence, as well as emphasizing the importance of changing and implementing legislation to officially declare the weed as an invasive species. Before this is done, no legal steps could be enforced around the management and removal of these weeds. Despite this, HRAC South Africa, CropLife South Africa, as well as Grain SA initiated various campaigns, from creating identification manuals, as well as training on these manuals, farm visits to the affected areas, as well as field trials in an attempt to best limit the spread of the weed to other production areas. The final focus was on informing the wider public of the weed through identification manuals, fact sheets, eradication plans, public press articles in popular press, including magazine articles, radio interviews, and scientific publications, in an attempt to notify the public and halt the spread of this weed. On this next slide, you'll see examples of informative documents compiled to raise awareness and advise end users with all facets related to Palma amaranthus. On the left-hand side of the slide, you'll see a fact sheet on Palma amaranth detailing integrated control as well as herbicide management of the weed in South Africa. In the middle of the slide, you'll see an eradication plan which was put together detailing ways to minimize the Palma amaranthus on South African soil. And on the right-hand side of the screen, you'll see that there were identification guides that were put together by Professor Charlie Reinhardt in his capacity with the SARI project. These are all tools in getting further information out to the public and ultimately the growers regarding this noxious weed. Despite all of these ongoing efforts, the weed seems to still be spreading to economically important production areas. But thanks to research efforts and various publications on, amongst other ways, to combat certain populations of this noxious weed, HRAC South Africa and CropLife South Africa have been hard at work fighting the spread of Palma amaranth. Following the positive ID of Palma amaranth in Potchefstroom earlier this year, CropLife sent out an emergency alert and continued applying pressure to get the weed classified as a Category 1 weed under the CARA regulations. This was then achieved in February of this year, which now allows for further legal actions to take place in restricting the spread of this weed. If you have a look on the slide, on the left-hand side of the slide, the first document was an example of the emergency alert informing on the spread of Palma amaranth around the summer rainfall region of South Africa. In the middle of the slide is a government notice from the Minister of Agriculture, Land Reform and Rural Development indicating that the Conservation of Agricultural Resources Act number 43 of 1983, has been amended to include Amaranthus palmyrea as a Category 1 declared weed, which is a big step in the right direction in combating Palma amaranth. And on the right-hand side of the slide, you'll see an article titled "A non-native Palma amaranth population in the Republic of South Africa is resistant to herbicides with different sites of action," which reports on research that has been conducted on the initial identified Palma population and its resistance to various herbicides. Thank you for taking the time to listen to the key focus areas of HRAC South Africa. For any further information, all the resources as discussed in this presentation are available or will shortly be available on the HRAC Global or CropLife South Africa websites. And for any further information, questions, or suspected herbicide-resistant cases, please contact myself or Mareka Craven at the email addresses as seen on the slide. Thank you.
Good morning, everybody. My name is Adriana Anthonissen, and I'm the chairperson of the Fungicide Resistance Action Committee, or FRAC, in South Africa. On this side, we can see the structure of FRAC South Africa. Recently, we decided to change our structure as we had a structure based on crop groups, which were small groups that met individually and discussed any resistance problems within the crop that they were dedicated to. However, the new structure is similar to FRAC International, with groups based on mode of action. So we have 3 groups at the moment in South Africa. We have an STHI group run by Rita van der Merwe. We have a QOI group run by Dirk Eys. And we also have a triazole group that unfortunately doesn't have a chairperson in place yet, but we hope to remedy that very soon. On the next slide, you will see our ambitions and our key actions for the future. Firstly, and most importantly, is monitoring of resistance development in our industry. One of the main drives of Frac South Africa is to bring together organizations within South Africa with the expertise and the equipment to do resistance testing, with the experience from our international colleagues who have been doing this for many years. This we will do by facilitating connections between local and international colleagues with the collaboration of CropLife. On the next slide, you'll see one of our other main focuses, which is education. Frac South Africa feels that we need to educate our industry on, firstly, what resistance management truly is, and secondly, where risks can be identified and how we can mitigate these risks. It is also important that we look at Frac International's guidelines for resistance management and communicate those to our industry partners so that they can be followed and we can be sure that we are doing resistance management correctly. This is one of our more important roles, even though not one of our major roles, and that is risk assessment. As we speak to the industry and we get feedback from our members, we can identify areas where there is a risk for resistance development. Once we've identified these risks, whether it's due to the actions of our industry, whether it's misuse of a single mode of action, we can identify this and we can try and put some mitigating actions in place so that this does not develop into a full resistance risk. On the next slide, you will see our next ambition, and that is to get collaboration within our industry. This is a quote from Henry Ford that says, "Coming together is the beginning, keeping together is progress, working together is success." This is important for us. We are coming together as Frac, as a whole industry. We've been keeping together for many years now, but we need to start working together more so that we can achieve a success and make sure that there is no resistance buildup. And if there is, that it's managed correctly within our industry, as this will be a benefit for everyone, whether we are farmers or chemical producers or agents selling these products. Thank you very much.
Okay, so thank you to Roleen, Cullen, and Adri for that update, and also for informing us all of the important work that you do. We really do appreciate it. Okay, so there are no questions after this round of presentations, but we do encourage you to channel those questions either to the contact details that were provided at the end of those presentations or also on the CropLife website. Okay, so we're going to be moving on to our next speaker, who's Dr. Nicholas Storer. He's the Global Seeds Regulatory Advocacy Leader at Corteva Agriscience. And his presentation this afternoon is going to talk to how plant biotechnology is part of the IPM toolkit. Nicholas's presentation is pre-recorded, but I think Nicholas should be online as well, just to answer one or two questions following his presentation. So I think that would be the cue to listen to that online presentation.
So firstly, my name is Nick Storer. I'm with Corteva Agriscience based in the United States. I lead our global seeds regulatory advocacy work. And I'd like to thank the organizers at CropLife South Africa for putting this conference together, for the invitation to contribute. By now, you'll have heard what integrated pest management is and how the practice of IPM is important in delaying and managing resistance to pesticides. Now I'm going to talk about how the products of plant biotechnology can and must be used as part of the IPM toolkit. So first I'll recap the principles of IPM using the classical pyramid model. So integrated pest management is the approach to protecting crops from pest losses that accounts for the entire agricultural production system and is focused on economic efficiency as well as long-term sustainability and compatibility with environmental goals. IPM emphasizes using diverse tactics in a holistic way to manage pests, incorporating practices to, on the left, prevent, monitor, and intervene. So at the bottom of the pyramid, we have measures to reduce the potential for damaging pest populations to develop. So making sure that the soil and field health is preserved, using cultural practices to minimize the potential for pest infestations, using pest biology and ecology to our advantage, using biological control, and in the center here, using host plant resistance. In the middle, we have measures to detect and monitor for changes in pest populations and crop injury. So monitoring the crop for signs of pest infestation, detecting and identifying the pests, and scouting over time to monitor for changes in pest population density and changes in crop injury. And finally, at the top, when necessary, the ability to apply pesticides and other control measures only when economic loss is threatened. To be successful, IPM must consider all of the pests that are present in the ecosystem and recognize that interventions to protect one pest may on one hand help in managing others, but in contrast may also exacerbate other pests. For example, the application of an insecticide to manage one pest may interrupt the biological control of another pest. So let's take a step back and look at the big picture. What are the goals of IPM? Well, first and foremost, the goal, of course, is to manage pests. The way pests are managed needs to also meet the objectives on the left. They must optimize crop productivity, be economically efficient, be environmentally sensitive, and be ecologically sustainable, as well as economically sustainable. So IPM is a way of working with the environment and with agroecology. Some of the possible outcomes are listed on the right. IPM may lead to increased farmer income, either through lower input costs or improved yields, or ideally both. IPM may lead to reduced environmental effects. It may maintain biodiversity and beneficial organisms. It may prevent or delay resistance, as you just heard. It may lower chemical residues on produce, which in turn can improve access to markets of those products. And it can enhance the responsible business for the industry, and also ultimately lead to enhanced consumer confidence. But again, those are possible outcomes of IPM. The purpose of IPM is to manage pests in an economically and environmentally sensitive manner. Let's just look again at the principles of IPM. The basic management unit of IPM is the agroecosystem, not individual fields. So any management action that does not consider the system as a whole may produce unexpected and even undesirable effects. IPM recognizes that most pest populations cannot realistically be eliminated and must be tolerated at some level. And intervention should be based on economic injury levels and action thresholds. IPM emphasizes strategies that avoid or inhibit the growth of pest populations as much as possible, and only when pest populations threaten economic damage or interventions considered. And I think really importantly, as we think about biotechnology, as the agroecosystems evolve, pest populations change, but the tools to manage them also change. And IPM must evolve with the agroecosystem and recognize that the tools such as biotechnology provide new options for IPM, and the classical approach to IPM that I've described can be adapted to work with biotechnology. And that's what we will look at today. So what are the properties of biotech crops that make them a good component of an IPM system? So first, let's think about insect-protected biotech crops. So this is your BT maize, BT cotton, and BT soybeans. These provide varieties that are resistant to insect pests. At the same time, they're protective of beneficial insects, and they reduce the need for insecticide applications. And we can also think about the other major group of biotechnology crops and traits being the herbicide tolerance traits. The ability to apply a herbicide to a crop and not cause damage to the crop and only control the weeds. This allows more effective weed control. It simplifies pest management, facilitates reduced till agriculture, and all of these we'll go into in a little bit more detail. And finally, at the bottom here, we can think about biotechnology used to deliver agronomic traits that can provide crops the ability to withstand and tolerate environmental stress such as drought, and creating a healthier crop, which in turn is able to tolerate pest attack under less favorable environmental conditions. So this is what biotechnology can bring to agriculture and can bring to IPM. And let's look at these in a little bit more detail. So first, let's look at insect-resistant crop varieties. It's important to point out that many of the properties listed here may also apply to native resistance traits, just as they do to biotechnology traits. But the level of protection and the specificity that biotech traits can bring is often significantly greater than native traits. So biotech insect-resistant crops express insecticidal proteins derived from naturally occurring sources. Again, consistent with the principles of IPM, using natural mechanisms to control pests. So the Cryo1 proteins, the Cryo2 proteins, and the VIP3 proteins are derived from a common soil bacterium named Bacillus thuringiensis. And that's the BT, and these are the proteins that are expressed in BT maize. These proteins are highly specific to the targeted pest species that feed on the crop and only affect a narrow spectrum of insects. They have a favorable environmental risk profile. Proteins don't bioaccumulate and don't present a hazard to organisms that aren't actually feeding on the crop itself. They're also harmless to beneficial organisms. All of the BT maize products, BT cotton products, BT soybean products that are available today have no effects on insect predators, on parasitoids, on decomposers or pollinators at realistic environmental concentrations. This means that they can fit very nicely into that classical IPM pyramid, preserving the biological control functions. And what we've seen over the last 20 years that we've been deploying these crops is in some cases that where they provide very high levels of protection against certain pests, they contribute to area-wide pest suppression. We have examples of European corn borer in the United States, which has been suppressed to such an extent by the use of BT maize that even non-BT maize farmers are seeing a benefit in reduced pest pressure. A similar situation with tobacco budworm in cotton in the United States, where tobacco budworm is becoming increasingly difficult to find when we do resistance monitoring. There's good documentation of suppression of Helicoverpa species in the eastern United States as a result of growing BT maize, where the vegetable producers are suffering less loss from Helicoverpa, from corn earworm, than they were prior to the introduction of BT maize. And recently there's even indications that Asian corn borer in the Philippines is being suppressed by the production of BT maize in that country. So they sound great, but it's really important to remember the BT crops are not a standalone solution. These crops are not immune from pest feeding. Firstly, the targeted pests must consume some of the plant tissue to receive a lethal dose of the insecticidal protein. And most of the pests that are affected by these proteins are not highly susceptible. And so they may require additional management to reduce population pressure. Importantly, also, only a subset of the pests is affected. The proteins I mentioned earlier, Cry1, Cry2, BIP3A, they all affect a subset of the Lepidopteran pests in maize and in cotton and in soybean. But they don't affect other groups of pests like beetles or aphids and thrips. And then there's always the potential for resistance to evolve in target pest populations. So it's very important when we deploy BT crops that we're monitoring for and taking steps to mitigate the potential for resistance evolution. So this means that we need to develop what we call best management practices in association with growing biotech crops. And these are based on the same IPM principles that we've already heard about. This is an important component of biotechnology in agriculture. So using those same cultural practices that reduce the intensity of pest pressure, continuing to monitor and scout just as with conventional crops, intervening, in this case applying insecticides, only when economic injury is anticipated, just as is done with a conventional crop, although because of the resistance that's provided against the insect attack. The need for insecticides is dramatically reduced. And then again, adapting those pest management practices to changes in pest pressure, invasion of new pests. And fall armyworm is obviously the most high-profile example of a recently invading pest that requires adaptation of IPM and biotechnology to manage it. And also, as resistance emerges to the BT traits, need to adapt the pest management practices to account for resistant populations as well. So just a word on resistance management. As you're likely aware, the BT crops require a refuge to be grown alongside them to provide an area where susceptible insects can survive and reproduce and reduce the selection pressure for resistance. Obviously, adding in alongside your BT crop a crop that is not protected with biotech traits creates additional complexity for the growers and requires some separate management practices. But what we've seen is, if for primary target pests, those that really drive the economic decision of a farmer to purchase the BT trait, those that are expected to be regularly present in the system and regularly require control in a conventional maize, in BT maize, the refuge can be very effective in delaying resistance. But as I said earlier, most primary target pests, BT crops are not high dose. The insects are not highly susceptible or highly sensitive to the BT proteins. So additional management is likely to be needed right from the start for those kind of pests that, again, are regularly present at damaging levels and only somewhat reduced by the BT traits. And then there's a whole suite of secondary pests which may be affected by the BT traits as well, but aren't reliably going to be present in the system. But growers will continue to need to be aware of the potential for them, scout for the secondary pests, and as necessary, intervene with insecticides. So the pest complex really needs to be considered as part of this IPM program. Okay, let's switch gears to the other major group of biotech crop traits, and that's the herbicide tolerant traits. These can also be seen as a foundation for IPM, and some of the properties are listed here. So just like with BT proteins, the proteins expressed for herbicide tolerance, which are actually act as enzymes, they're derived from naturally occurring sources. So an example of EPSPS, which is the enzyme that gives tolerance to glyphosate, was derived from an agrobacterium strain, very commonly present in the soil. Enzymes themselves present no environmental risk. Their activity is biochemical in nature, not biological. The ability to manage weeds in the season means that pre-planting tillage can be greatly reduced. So they do really enable it, and we've seen over the last 25 years how no-till and low-till agriculture has come to dominate in countries where herbicide-tolerant traits are used. And this means that the health of the soil and the soil structure can be maintained across seasons. These traits improve the ability for farmers to be flexible in the timing of their herbicide application. Instead of being concerned about the herbicide injuring the crop, they can really target the applications for when weed control is really needed based on the presence of the weeds and the density of the weeds, rather than thinking about the crop. And this means that they can also enable later herbicide applications. And there's a beautiful study from the UK from around 2000, where they looked at using herbicide-tolerant crops and the ability to allow weed populations to develop and then be sprayed with glyphosate, and saw a great increase in the biodiversity in those fields, as both the living and the dead weeds can provide habitat for beneficial organisms. And another big advantage in this flexibility in herbicide applications is it saves labor and it saves fuel with fewer passes across the field. This means less disruption to natural processes and contributions to reducing the effects of reducing carbon emissions and the effects on climate change. Herbicide tolerant crops aren't a one size fits all. They're not as simple as perhaps a grower would like. Best management practices based on IPM again are important. First, and probably fairly obviously, use the right herbicide. If you have a glyphosate tolerant crop, it's glyphosate that you should be applying to manage the weeds without harming the crop. But you can adjust the application rate and timing according to weed pressure, again without the concerns that the higher rates may affect the crop. Applications in favorable weather conditions are also important to avoid off-target effects and runoff. Avoiding applications that harm natural vegetation at field margins. Natural vegetation can be very important for maintaining biodiversity, particularly in the natural enemies of the crop pests, and that's where we link back into the insect traits. We can preserve the biological control function. Importantly, selecting and using herbicides with different modes of action within the season, both to manage hard to control weeds that may not be easily controlled with the main herbicide, but also to counter the development of resistant weeds. So it's very important that a grower planting a glyphosate tolerant crop doesn't only apply glyphosate year in, year out, because that will select for resistance, as we've seen in the United States and South America. Growers need to be using a diversity of herbicides across the season. Scouting the fields after application for weed escapes to make sure that if those escapes are a result of resistance, that they can be taken care of. And then, of course, always following label instructions and wearing personal protective equipment. And then we can put these two crop trait types together in a single crop through stacking. Growers really are looking for the benefits of insect resistance and the benefits of herbicide tolerance in one plant. And through just conventional breeding, we can combine these traits. And this leads to certainly simplification of some aspects of IPM, but IPM still remains important to achieve the full benefits. And then just a word on pyramiding of traits, which is a special form of stacking where the traits that are being combined together serve the same function as one another, but through a different mechanism of action. So multiple modes of action against target insect pests provide additional control, additional protection from resistance development, and in this case can reduce the size of the refuge needed to preserve the durability of the technology. And then in the case of herbicide tolerance to multiple different modes of action allows growers to use different herbicides within the season, and again provide protection from resistance development, as well as control a broader spectrum of weeds. So let's come back to the IPM pyramid that we started out with, and how do the biotech traits really fit within this? So firstly, let's look at the herbicide tolerant crops. They, I said earlier, because of reduced tillage, they can protect soil and field health and reduce nutrient loss. The timing and rates of herbicide applications could be more flexible, enabling the interventions to be more effective and more economically efficient, driven by the status of weed populations rather than the sensitivity of the crop. For insect resistance traits, these can be regarded really as part of the foundation of the IPM pyramid as host plant resistance. They also facilitate biological control, being non-hazardous to beneficial organisms, and they in turn reduce the need for insecticide applications for the intervention at the top of the pyramid against the targeted insect pests. And then, of course, of critical importance, other IPM tools must also be used. In particular, pest monitoring and scouting are just as important in a biotech IPM system as in a conventional system. So let's put it all together here. It's looking at integrated pest management and how biotech crops contribute to IPM. And so on the left really is a series of steps that growers should be taking as they plan for and manage pests across a growing season. And on the right is how biotech crops can contribute to that. So firstly and foundationally, knowing your environmental conditions, knowing your pest complexes, knowing what challenges you're likely to face in the season. And then secondly, choosing crop varieties that thrive in that local environment. And clearly, when biotech crops are available, looking at the insect resistance traits, the herbicide tolerance traits, and the stress tolerance traits that a grower has access to improve the way that the crops thrive. In IPM, planting at a time that maximizes availability of natural resources and minimizes pest pressure. That applies equally, if a biotech crop is being grown. And maintaining a healthy crop clearly is vital to IPM. So it's important to understand how the biotech traits that are included in the crop contribute to crop health. Monitoring and scouting fields for pest, insects, weeds, and diseases. In the case of crops with insect traits, they're less likely to have high pressure, but it's still important to continue monitoring and scouting. Applying pesticides only when economic loss is threatened. Again, insect traits require less pesticide application because of the protection provided by the trait. And as we've discussed, herbicide tolerance allows flexibility in timing and rates to really target the weed populations. Choosing effective products with the least impact on beneficial organisms. To extend that, in the case of herbicide tolerance traits, to choosing products that actually match the tolerance trait. And then in all cases, following pesticide labels and using PPE. So I've tried to make IPM with biotech crops appear to be as simple as I can, but we must recognize that IPM does introduce complexity, and it does require knowledge and expertise, and it requires engagement of everyone that influences crop production. It's not just a farmer left to work it out for themselves. So on this slide, I'm showing the recently updated IPM model developed by Surendra Dara in the United States that explicitly recognizes IPM must account for economics, for the environment, and social responsibility. And in turn, it must involve not just producers, but also sellers and consumers. It's perhaps part of our responsibility in the crop protection industry to make sure that all of these pieces of the puzzle fit. So biotechnology can increase the demand for knowledge, it can increase the need for planning, and certainly it raises societal considerations that are different from conventional crops. And transparency becomes really important. So the farmers and the developers of these traits must engage with food manufacturers, with supermarkets, and with consumers and the public in order to build trust both in the technology itself, but also, I think, critically, how the technology is used to improve agricultural production, as well as improve economic and environmental sustainability. And I'll just wrap up with my take-home message, which is really IPM stands as a key approach to managing pests, preventing pests, monitoring, and interventions. So biotech crops enable productivity improvements and have a smaller ecological footprint than most other crop management practices, and therefore can enhance the success of IPM. And with that, I will thank you for your attention and look forward to any discussion.
Good afternoon, Nicholas. I believe you are joining us online, or should I rather say good morning?
It's morning here. Hello to you too.
Okay, so firstly, thank you for that insightful overview on how biotech fits into the IPM system. Definitely some interesting points that you've raised there. We will take some questions from our audience, if there are any. I don't see any show of hands, any takers? Oh, there is one. Okay.
Good afternoon and good morning, Nick. Thank you for representing us in this Congress. I have two questions. One of the things that actually came up in CropLife conference in Europe was that the biotech that we're developing today is mainly maize, cotton, and soya. Do we have plans to actually move this technology to other crops, to actually put some advantage for the farmers in other sectors? And then another thing that I would want you to clarify also, one of the things that was discussed in the conference was the gene editing and biotech. Is gene editing bringing more? And it seems as if in Europe, it's actually being seen as one. Can you clarify that for us? Thank you.
Yeah, great questions. Thank you. So firstly, yes, the multinational companies, which I represent one, certainly focus on the global high-value crops, maize, cotton, and soybean. But there are a lot of efforts underway, either in the public sector or in public-private partnerships to expand the range of crops that are benefiting from biotechnology. So there's disease resistance in cassava. There's papaya in Hawaii that is resistant to disease. There's a lot of work going on. I'm sure you're all aware of the Golden Rice Project as well, which is not bringing pest management benefits, but certainly very important human health benefits. So there is a lot of work going on in other crops. Again, the multinational companies are focusing on the largest acreage crops. I think we'll see progress in additional crops in the future. Touching on the gene editing question, I like to think of two categories of these tools. One is moving genes among species, and that's what I've been talking about in my presentation. Moving a gene from a bacterium and putting it into a plant. So those are really the transgenic applications. Using gene editing tools like CRISPR, you can use those same tools to also move genes among species, but they provide additional flexibility to edit genes that are already in the species and not have to move genes around. And I think that the implications of gene editing used in that way, it's far more similar to conventional breeding. The outcomes are the same in many cases as can be achieved with conventional breeding, but it can happen a whole lot more quickly and with much more precision. So what we hope to see in Europe and elsewhere is this continued recognition that gene editing is not the same as transgenics. GMOs are really the transgenic end of biotechnology. Gene-edited products are really more closer to the conventional breeding and probably improved over conventional breeding, and should be associated less with the concerns that some people have raised around GMOs.
Okay, thank you for that response. And maybe just to add on is to say, in terms of on the African continent, we are seeing insect resistance also being approved in Nigeria for cowpea, and we are looking also at developments in cassava in Kenya. So I think definitely Africa is moving also towards the adoption of the technology, but geared more towards crops that are of economic importance to those populations. And I think I don't know if there are any more questions from the auditorium. Maybe I could just add on before letting you off the hook, Nick. Just to add on to that, we are seeing adoption of BT crops in African countries, select African countries. Just from your experiences at Corteva, the adoption of these crops does, or a key IPM feature of adopting these crops does require, strong focus on resistance management. From your side, are there any, I would say, best practices or key learnings, in terms of what you could share with us where BT technology is now coming online, and it's a new experience for some of the smallholder farmers that are adapting the technology. Do you have any insights to share with us?
I think it's critical, and I touched on it in my presentation, to recognize that the BT crops are one part of, or the BT traits are one part of the crop and the crop management system. As fall armyworm has invaded and spread through Africa and Asia as well now, a recognition that BT crops bring a high level of protection from fall armyworm, but again, they're not immune. We know that resistance can develop. It has developed in the Americas in fall armyworm to these BT traits. And farmers really need to continue to monitor their crops and be prepared to intervene with insecticide applications or other management tools when indicated by the level of pest damage that's occurring. So again, these are not a silver bullet. They're an additional tool that farmers can exploit and reduce some of the burden on the need to apply insecticides. But see these as part of the whole picture, not as a standalone.
Okay, thank you, Nicholas, and thank you for making yourself available and lending your expertise to the discussions this afternoon. I don't see any more questions, so I guess that would be it from our side. But thanks again for your participation. And so we'll move on to the last presentation of this session. And we will be hearing more about how biologicals fit into the IPM toolkit. And that presentation will be given by Sean Thackeray, who is the Business Development Manager at River Bioscience. This is again a pre-recorded presentation, so please do listen carefully and jot down some questions if you have any for Sean, who will take a few questions after his presentation. So we should be loading up that presentation right now.
Good afternoon, everyone. Thank you very much for giving me this opportunity to share some of my thoughts with you. My name is Sean Thackeray. I work for both River Bioscience and Exit as part of the RBX group and look after the product development and business development portfolios. So today we're going to be having a very brief look at biologicals as part of the IPM toolkit. We obviously need a lot longer than 18 minutes to do this topic significant justice. So it's really just going to be an exposure as to how biologicals can be used within an integrated pest management program and some of the mindsets that go into structuring a successful IPM program. So I'm sure this would have been touched on earlier on in the seminar, but let's just have a quick recap on the definition of IPM. So it's always quite nice to default to what the European Commission regards as the definition of IPM, because this drives your new farm-to-fork strategies and the European Green Deal that we've seen coming into our recent agricultural mindsets. So the key components really is that it's a careful consideration of all available plant protection methods and the subsequent integration of these methods. And this is to ensure that what we're doing is both economically and ecologically justified to reduce or minimize the risks of both human health and the risks to the environment through crop protection practices. And one wants to ensure that we are striving towards the growth of a healthy crop with the least possible disruption to the agro-ecosystem, and also encourages the natural pest control mechanisms that are now available to us in the modern era. So on the right-hand side of this slide, you'll see that CropLife has a fantastic diagram of an integrated pest management, let's say, portfolio or mindset. And one of the key things that I'd like to bring our attention to is that there's three components. So the first one is a prevention. So these are all of our agricultural practices that prevent the requirement for additional inputs. We then have various methods of observation, and then right in the middle we've got an intervention should we need to go over any of our economic thresholds. Now, this economic threshold is quite an interesting, perception in South African agriculture, because in my experience, IPM is most dominant in environments where we are exporting to first world countries, and that's normally within our high-value fruit and nut tree crops. And the economic threshold may be lost and almost exchanged with a phytosanitary threshold. And this almost undermines the concept of IPM. And it's something that we all need to be extremely cognizant of going into the future. So some key challenges of adopting IPM. This is a fantastic paper that was published last year that looks at challenges from a cultural, a knowledge, a user preference, industry, technology, and policy perspective. But one of the key things that came out to me in this was the significant difference in the types of challenges within these pillars between the northern and southern hemisphere. And one thing that we all need to be very cognizant of, especially when bringing new biological products to the market, is that one cannot just address a challenge in the northern hemisphere through, let's say, developing a certain type of knowledge, and then try and shift that knowledge to the southern hemisphere and expect to overcome the challenge that one did in the north. They're very different environments, and one needs to take a very focused approach to the challenges that one has to overcome within a specific geographical area or within a specific crop or culture that biologicals are trying to get incorporated into an IPM program. So when we start having a look at the IPM toolbox, there are three core areas that one needs to cover to implement an IPM program. The first one is knowledge of the target pest and the pest ecosystem and the overall agricultural ecosystem that this pest management practice is trying to take place in. So the types of knowledge areas that we would look at specifically with a focused pest would be the life cycle. This could vary between crops and between cultivars. This could vary between crops and cultivars. We would look at pest behavior, the seasonal cycle. This could be influenced by the immediate surrounding environment and also environmental parameters within the area of focus. We would look at population dynamics within that pest species. And then finally, the interactions that we see between this pest and other potential pests or beneficial organisms, as well as how our overall spray program can have an interaction between these different target and non-target effects. The next level is decision making, and this is driven by decision making aids. Some examples here is making sure that we've got the proper pest identification. What pest monitoring methods are we using? Are we only using scouting data, or are we able to monitor flight peaks through the use of cards or pheromone traps? There's also environmental monitoring, so this would be using degree day models. We would look at economic injury levels or some phytosanitary levels, which is more common in our part of the world. And then we would have action thresholds, where when we exceed one of these thresholds, we would start to do something about it. Then we need to have a look at the toolbox of pest management tactics that are available to us. And this consists of biological controls, cultural controls, mechanical controls, and chemical controls. And how do we integrate all of these together for sustainable crop production and crop protection? When we have a look at the biological products within the toolbox, we really have a broad range of products available to us. Now, one of the main reasons for this broad range of product is that biological products are often quite species specific or perform well within niche type environments. It's not something that one can just apply to a broader landscape. It needs a lot of thought and a lot of research into finding out exactly what is this niche that this specific active ingredient or type of product can really deliver value on farm. There's three overriding categories of biological products. This includes biofertilizers, biostimulants, and biological control products. So Biofertilizers really consist of microbials used to enhance plant nutrient uptake from soil. Nitrogen-fixing bacteria do make up the largest component of this group. Others include mobilizers of specific nutrients such as zinc and sulfur, and also mycorrhizal fungi. And biofertilizers are regulated under country-state fertilizer regulations. And we know that we've just gone through a revamp of our local regulations in South Africa. The next category is biostimulants. So in this one, seedweed extracts make up the largest component of the group. There's also microbials. This is primarily bacteria, and it's often used as seed or soil treatments to aid nutrient assimilation. We then have organic acids, and these are humic and fulvic acids used as soil amendments, and these are formed by the microbial degradation of plant matter. And the definition and regulation of biostimulants is still under development in many parts of the world, but we have made significant progress in this in South Africa in the last few years. The next category is biopesticides. Now, biopesticides are derived from natural materials such as plants, bacteria, and certain minerals. Biopesticides target specific pests and are inherently less toxic than synthetic pesticides in most cases. The categories within biopesticides are firstly biochemicals. This includes plant extracts. This is minerals and others, plant growth regulators, potentially semiochemicals and organic acids. And plant extracts make up the widest segment of this specific group. We then have semiochemicals and specifically pheromones. And pheromones have the largest number of actual product types because these are so species specific. So basically each pest that one is wanting to target will have a specific pheromone associated with it. And then some of the largest challenges of plant extracts is the manufacturing and the consistent quality required for a commercial type product with an active ingredient. Then moving on to microbials. This is also quite a big section. We have bacteria, fungi, virus, protozoan, yeast. In more recent times, lipids have become another prominent area of research. Bacteria followed by fungi make up the largest groups of these types of products. So it's about over 90% of the commercially available products consist of both bacteria and fungi. And microbials are the largest market of biopesticides, and this is estimated to be about $1.3 billion if you go and have a look at the Dunham and Trimmer reports from the last few years. And some of the biggest challenges for microbials are formulation related. So how do we ensure that we're getting the longest shelf life in a non-refrigerated environment? Majority of these microbials need to go through the supply chain in a refrigerated manner. We also need to focus on stability and lastly performance enhancement in various environmental conditions, because some of these microbials do face significant environmental degradation once they're applied. When one looks at macroorganisms, so this consists of insects, mites, and nematodes. Insects followed by mites make up the largest groups. They're unique in that it's a live organism in the forms of egg larvae of pupae, which is used for subsequent control of another target pest. And the most important challenge with macros is logistics. So how do we ship these living or live organisms that have a really limited, let's say, period of life around the world, getting to the farmer, getting through the farm gate and applied in time for the grower to derive the most value out of these specific types of products? Now, this is quite an interesting thing to consider when we start talking about sustainable agriculture. Yes, one can start using macrobial type products, and we are using an environmentally friendly product. There are no residues associated to it, but there's potentially a massive carbon footprint that goes with shipping these sorts of insects around the world. So now that we've been introduced to the various types of biological products that are available, and we've been exposed to what the IPM toolbox looks like, I thought that the best way for us to try and understand how we can start to put all these moving parts together is to have a look at a case study. And the best, in my experience, the best way to look at case studies is where there's a significant amount of information available. So for this, I've chosen false codling moth. It's an insect, a pest that we are intimately familiar with here at River Bioscience. And it's also a very broad-ranging pest of citrus, avocados, capsicums, stone fruit, table grapes, and tree nut crops. Now, these are all pretty much exported from South Africa. As an example, citrus alone brings in about over 30 billion rand each year into the country from its exports. So market access is a very important component of citrus exporting. Now, false codling moth is one of our largest challenges for maintaining market access, because from 1998, we've seen an increase in the number of countries, and these are key markets for us, where FCM is now regarded as a regulated quarantine pest. And this fundamentally undermines the practice of economic thresholds for FCM. We're now working on phytosanitary thresholds, and when you consider just the quantum of crops that we export into the markets listed below here, one interception is too many. So there's been a complete systems approach developed for false codling moth. And what we'll be focusing on today is the in-orchard part of that systems approach. At a quick overview of the life cycle itself, you'll see that we start off with an adult. This adult then goes and lays or oviposits its egg on the fruit or nut itself. And then once this egg hatches and the neonate larvae exits the egg, it starts to look for a suitable site to burrow into the fruit. And once this larvae is penetrated into the fruit, you lose all opportunity of control other than cultural control measures, because this larvae is now protected by living within the fruit. Your next opportunity for controlling this pest is in its soil-dwelling life stage, where wandering fifth instar pupa or wandering fifth instar larvae and pupae will spend an extended period in the first couple centimeters of your soil layer or leaf litter layer. So when we have a look at the biological toolbox for false codling moth, I've split it up into the different life stages. So from an adult perspective, there is a sterile insect technique program that is available in South Africa. We have various mating disruption products available. We have an attract and kill product, and there are a few lures on the market, and these are pheromone lures, which allow us to monitor the population phenology over the season. And we can start using this information to inform our pest management practices and structuring our IPM programs. Moving on to the egg, so there is an egg parasitoid that is available. When we have a look at the neonate larvae, so these are the larvae that have just hatched, and then we're wanting to control them before they go into the fruit. The majority of the products used here are virus-based products and entomopathogenic fungi. And then when we look at fifth instar larvae and pupae, so this is the soil life stage, there are some entomopathogenic nematodes that are available. So over the next few slides, we'll look at each one of these life stages and the potential biological toolbox that could be used to target each one. So moving on to the adult life stages. So as an example here in the top left-hand corner, you've got what a typical FCM flight activity looks like over a season. And this information, which is critical to pest management practices, is gathered through the use of pheromone lures. Now, in the bottom left-hand corner, this is an example of efficacy gained through the use of mating disruption and attract and kill. And what we can see is that we get an efficacy ranging between 30 and 55% within this specific trial through the use of either mating disruption or attract and kill. And then the next option, our sterile insect technique, is widely used in the eastern, western and northern Cape. There's about 16,000 hectares of susceptible FCM crops under the SIT program. And this graph doesn't give you a season's data, because the benefits gained from sterile insect technique is compounded interest. So we suppress the population over time so that we can soften the overall inputs into our integrated pest management program. So an important measure here is infested fruit. Now, this is data from one of the valleys where we've been evaluating FCM levels since before SIT, and then all the way up to the 2021 season. And what you can see is that the yellow bar pre-SIT was almost 1.7 fruit per tree per week. Now, this is a significant amount of infestation for a grower to manage within a phytosanitary pest environment. And what you can see is that after almost 11 years of implementing the SIT program, we have pretty much made infestation negligible at an area level. Yes, there will still be individual orchards within this overall area that may still have infestation. What you can see there is a significant reduction on the incidence of infestation within an area. Now moving on to the egg life stage. So here we've got a real neat organism called Trichogramatolia Kryptophilia. So it's an egg parasitoid. It is endemic to our part of the world and is available through a few outlets in South Africa. One of the biggest challenges with using parasitoids is that they're very susceptible to synthetic pesticides, which are included in Canada spray programs. So this limits the use period to certain times of year. When we start looking at specifically citrus production, you've got it in the northern parts of the country. You have calendar citrus black spot sprays, and these calendar citrus black spot sprays generally drive what an overall IPM program looks like. And it's not easy or not very effective to be releasing these parasitoids while you're still having frequent CBS applications. So that potentially compromises the ideal time of initial release, and one now needs to shift this release to a different time of season and understand what the impact of that is at an orchard level. But in essence, this is some work done on the right-hand side by Dr. Sean Moore at CRI. You can see there that when releasing parasitoids in an augmented manner over a 18 to 19 week period, fruit infestation was able to be reduced from about 3.5 fruit per tree per week, all the way down to less than 0.5 fruit per tree per week. And this is just with one single organism. So it's a fantastic option to target the egg life stage. Moving on to the neonate larval life stage. So this is just before the larva penetrates from egg hatch to when it penetrates into the fruit. And it really is the only option to protect the fruit going into the packhouse. So when we start considering the phytosanitary components of false codling moth, we do not want any infested fruit going into the packhouse. Now, the use of mating disruption and the use of trichogramma don't necessarily protect the fruit. They suppress the overall population so that one can get the highest level of efficacy possible out of our other inputs, which are applied as foliar sprays, and in essence limit infestation taking place. So there are a few options available here. There are some virus products, there's bacteria, and there's entomopathogenic fungi. However, the frequency of application required for efficacy is generally a driving factor for use here. Certain active ingredients require frequent applications, normally 3 to 5 applications, 7 to 10 days apart, to give the sort of efficacy required to manage a phytosanitary pest and limit infestation going into the packhouse. Now, obviously, in an environment where a producer has 400, 500, 600 hectares and they're trying to get through their orchards with a spraying machine prior to harvesting, it's very difficult for them to implement those repeated applications in such a short period of time. So what we see is that certain products are being used later on in the season compared to early on in the season. And a lot of virus products are favored as a pre-harvest application because they come with a single application that gives fairly good efficacy, and they also don't take any residues into the packhouse. And one major thing that we've got to consider with these biological products included in foliar applications is that they do have environmental degradation over time. So in my opinion, it would be almost impossible for someone to make a statement along the lines that you're guaranteed a certain level of efficacy in terms of fruit protection for a certain period of time, for example, 6 or 8 weeks. What we see is that over time, there is a reduction in efficacy due to environmental parameters. Now moving on to the soil dwelling life stage. So this has been an area that hasn't necessarily been a major one of focus due to the expense of products that can be used in this area. So there are a couple of entomopathogenic nematodes that are registered for use against false codling moth. But when one looks at that specific life stage and the timing of the program, as well as the environmental conditions of both the orchard and the substrate in which you're applying, it can be a slight hit and miss exercise, and it takes a lot of commitment by the producer, the supplier, and the technical advisor involved to ensure that the grower is getting the best value for money when using these products. But what you can see here is that this is from Mullen and Moore from 2016. They showed that basically after 21 days and 35 days after application, you can get over 60 and 80% mortality of FCM larvae using entomopathogenic nematodes. Now, the bottom graph is just an example here of some research that's come out of the Center for Biocontrol at Rhodes University, is looking at a different mode of action here, or a different product type, and this is through using soil-dwelling entomopathogenic fungi. So what was really interesting out of this work is that they evaluated 2 commercially available EPF products, and what they found is that when applied to soil at the registered commercial foliar rate, they didn't add much benefit to the grower. And one needed to significantly increase the rate per hectare, and also use a isolate that was found or isolated within the local environment to start getting sufficient reduction in FCM infestation from soil applications. And what you can see here is that this ranged from between 23 and 60%, depending on the rate and also depending on the isolate that was used. This is really a framework for how a producer would start to structure an IPM program using the biological inputs that we discussed in the previous slides. So the first thing that one would do is start looking at monitoring. How do we monitor adult activity? And we do this through the use of the pheromone lures that we introduced as part of the semiochemicals. Now, this will give us some interesting data, which an example is shown in the bottom part of the slide, on when our key areas of flight activity are. Now, once we've got an understanding of our key areas of flight activity, we can start understanding when we're going to need to control the adult, when the pupae may be susceptible to control in the soil, when these adults may be laying eggs, and then when these eggs may be hatching into larvae. So once we've got our monitoring system set up, a core component for a successful IPM program, especially using biologicals, is our cultural practices. Now, we haven't spoken much about that because that's not the topic of this presentation, but I just want to highlight that implementing a biological IPM or biological tools within the IPM program relies on good orchard sanitation practices. Once we've got a strategy for putting this in place, we can start looking at how we're going to be controlling our adults now, or suppressing the adult population. Now, one would traditionally do this between October and April, because in the months of May through to September, it may start to get too cold for the use of semiochemical-based products, and also the use of sterile insects may be confounded by your cold nighttime temperatures. So when we have a look at that October through to April period, we need to decide, are we going to be using an attract and kill product? Are we going to be using a mating disruption or SIT? And the overall goal of that adult suppression is to reduce your population as much as possible so that you get the highest utility or the highest return on investment for any other control or intervention measures that are put down over and above your adult control strategy. Because this is probably going to be the most expensive part of your RPM program. We can then start looking at the release of egg parasitoids, and this would be augmented. One wouldn't want to start this while you are still doing a calendar fungicide program, for example, citrus black spot. So the timing of this could be anywhere from February through to May. Now, once again, this is not going to limit. It's going to reduce the overall population. It's not going to protect your fruit from infestation. Then we can start looking at ideal times for soil applications. Now, this is a fantastic time for this would be prior to starting off the next growing season. So doing an August or September application, you're catching your overwintering larvae, your overwintering pupae. So once again, the use of egg parasitoids is not going to necessarily protect our fruit from infestation to the levels required through phytosanitary pest management. The next option that one has is controlling the soil life stage. This can be done through the use of entomopathogenic nematodes, and a fantastic time to do this is in August and September, once our previous season has ended, and there may be quite a lot of overwintering pupae within the soil, and one wants to do a population knockdown before our first flight peaks start happening in October, and before we start doing area-wide management focused on the adult population. And then the last option available to us is inputs focused on the neonate larvae before fruit penetration. So the timing of these needs to correlate with flight peaks so that we have the most viable active ingredient on the surface of the fruit as possible, timed for when our eggs are hatching. Then one would start looking at cultivar susceptibility and harvest periods and try to work out a strategy that limits infestation going into the packhouse. So when we start having a look at the compound effect of RPM, so we've discussed that RPM consists of various different control measures. So what can our RPM program almost give us before we even start going into the packhouse, where we would start sorting out infested fruit from non-infested fruit? So if we started off with 100% infestation, our first part of the RPM program is orchard sanitation. And let's say that we get a 50% reduction in pest pressure through just good orchard sanitation. We can then use parasitoids, and this would reduce it by a further 50% at a minimum. Then incorporating SIT, mating disruption or attract and kill, we can reduce this by another 50%. We could then use a baculovirus, and this would reduce it by at least another 50%. And then lastly, a chemical spray, should we need, and this would have another 50% reduction in a worst case scenario. So what you can see here is a very compounded effect of what you can see here is a very conservative, let's say, expectancy of what efficacy we would get from these various different parts of our RPM program. And at the end of the day, we've been able to reduce FCM infestation going into the packhouse by 97%. And that's assuming a 50% efficacy, which is quite low for all the various inputs here. So to finish off, I'd just like to share our internal philosophy here at River Bioscience on how we approach an RPM program. So the first one for us is that one needs to understand the risk on farm. Their farms are various sizes, they're in various geographical scenarios. There may be a high level of alternate hosts surrounding the property. There may be no alternate hosts surrounding the property. We may have a range of cultivars. There could be one or two very susceptible cultivars, or there could be non-host cultivars within the overall orchard infrastructure, which may erode on the efficacy of our area-wide management practices. So once we've got this risk on farm, we can start committing to an upfront program. So this is something that we're going to do regardless of whether we see high or low pest pressure. It's an upfront commitment, and that's how we start to manage our agricultural input budget for a specific pest. Now, there are three different components here that one needs to consider when looking at a foundation program. The first one is risk management. So this is influenced by the risk of the farm, really the cultivar and the fruit type and the pest pressure, and it's also influenced by the market that one is exporting to. Some markets may have FCM as a phytosanitary regulated pest, other markets may not. Then we need to look at residue management. We've seen a lot of downward pressure from our European retail outlets, limiting the number of residues that one is able to have on their fruit going into a market. This is going to fundamentally impact what products that one can use and how one structures a spray program. And then lastly, price management, because we can't, IPM and sustainable agriculture needs to consider both people, profit and planet. And if we are producing our agricultural products in an unprofitable manner, then the business is not going to be sustainable in the long run. The next one is to establish these site thresholds. So I call them site thresholds rather than economic thresholds, because economic thresholds may have no relevance to managing phytosanitary pests. So a site threshold would be something that only really the producer or someone who's intimately involved on farm would be able to establish. So looking at their historical information or insight into the area that they are producing in, what triggers an additional or corrective action? Is it out of season rain? Is it a few hot days in May that they've seen in the past? If this happens, we have higher FCM pressure going into June, July. And once one's got these site thresholds in place, the producer or the farm manager needs to commit to some sort of intervention should these site thresholds be breached. And this could be additional orchard sanitation, it could be a commitment to additional sorters with fruit going into the pack house. It doesn't necessarily always have to cost you money or result in additional ag inputs being applied to the crop. And then we need to allocate our resources wisely. So considering all of the above, what products are we going to select that gets us to our market in the most efficient and effective way possible? Once we've selected these products, we need to understand what the label says and how the label instructs the end user to get the best results possible. Because at the end of the day, these labels are what drive efficacy of a product. And if we are not at least aware of the parameters discussed within the label, how do we make an intelligent decision to use them effectively in the field? And then the last one is incentivizing staff. How do we incentivize our staff to ensure that they are doing the best thing possible for an IPM program to be successful? And then lastly, realistic expectations. So one thing that we found heavily in our business is that when a producer or farm manager commits to a large expense of an area-wide program, they start getting an expectation that this is going to solve all their problems. Well, as we saw earlier on, through area-wide management, we're only addressing a very small part of the season, but that investment is to ensure that we're reducing the population later on in the season so that any other inputs are more effective than what they would have been under very high pressure. So whenever discussing an integrated pest management program with a producer, if one is cutting corners or not committing to a baseline or foundation program, one needs to ensure that they have realistic expectations of what the results are going to be. Because the worst thing that we can have for IPM going into the future is growers writing off certain products because they were supposed to be used in an IPM program and they've actually been used as a standalone silver bullet. So thank you very much for the opportunity to discuss this with you today. I look forward to hopefully interacting with you in the panel session, and hope to see you out in the field.
Good afternoon, Sean, and welcome to the IPM session this afternoon. I'd just like to thank you again for the presentation, the comprehensive overview of biologicals and how they are used in the citrus industry to tackle false codling moth. I think I'd just like to take a scan of our auditorium to see if there are any questions from our audience. I see there's a few hands, so maybe we can start with you, Gerard.
Sean, good afternoon.
Afternoon, Gerard.
Looking at your last slide, that slide which you showed the reduction of the false codling moth using the different biologicals and the eventual chemical control. From your personal perspective, give us your opinion. Is biocontrol at all compatible with the use of synthetic and natural pesticides? Thanks.
Gerard, that's an essay question, and my talk already went on long enough. So my opinion is that as soon as one gets away from calendar spray programs, specifically calendar fungicide spray programs, it is possible to adopt a significant biological control program on your farm. As long as our citrus black spot calendar spray is taking place, it's going to be very difficult for IPM to be implemented as intended from the beginning.
Okay, thank you. I think there was another question in the audience.
Hello, Sean. Chris, I don't know if you can see me.
I've got a comment. I recognize the voice, yeah.
And it's in two parts, really. I guess the second part is a question. One of the things we encounter a lot in the field is similar to what you put up as a suggested IPM program that you could present to a farmer. And this is very often put forward by a consultant, for instance, and their names have come up earlier in the day for being irresponsible sometimes. But as a suggested solution where there's not necessarily a registration yet, and I'm not sure if your entomopathic fungi are registered. So that's my comment, and I don't know if we have a way to counter that, but the question is, in terms of macrobiologicals, are we any closer with all the hindrances and the inefficiencies at the registrar's office of getting macrobiologicals registered? And do you think that's going to happen at all? Is it something that's being pushed from SABO's side? Maybe Andrew Bennett should have asked.
To answer that, I'll have to stir the pot a bit. So I didn't want to incorporate any of our own river bioscience information within that presentation, or else it could have just sounded a bit like a marketing spiel. But I can tell you that both of our EPNs are now registered, and not necessarily commercially available due to the fallout in the supply chain we've seen from Europe. But yeah, both the SF and the HB are registered with Act 36. And as far as the other macrobials code, let's say your insect biocontrol agents, that's also something I can't really give a generalist opinion on. I can tell you from our experience, we do have 4 different macrobial insects now registered with Act 36. As far as the other input suppliers go, I'm not sure how they're progressing with their registrations, but it is time consuming, it is expensive, but it's what's required to be compliant. And it's a difficult one where the majority of the industry is operating outside of that compliant ground, because then there's no real incentive for the regulators to clamp down. And the only way we're going to get some momentum is if the whole industry decides that this is the way we're going to go. We're willing to get regulated in a small way, and we're going to write our own story rather than having some guidelines that are just being applied without deep consideration into how applicable they are. Hopefully that answers your questions. Any follow-ups?
Okay, now I think that concludes all the questions from what I can tell. So thanks again, Sean, for participating this afternoon. I think that essentially concludes our IPM session for today. So thanks to all our speakers for your participation and excellent presentations. Also, thank you to our online participants and those of you in the audience, and thank you for staying the course. I think right now I'd just like to hand over to Rod Bell, who's going to wrap up the day's proceedings for us.
Thanks, Chantel, and thanks to everybody who's weathered the whole day. There's been one hell of a lot of information that was thrown around today, so thank you. I'm just very briefly going to summarize some of the key points I'm taking away. We started the morning off with Julia, Laurie, and Samira from CropLife International and CropLife Africa Middle East respectively, providing us with an excellent overview of the EU Green Deal, the possible impacts on South African agriculture, how industry has and will continue to engage with policymakers in the EU to try and mitigate any negative impacts that the EU Green Deal is going to have on our country. We then had an excellent local flavour from Cobus, giving us a specific view on the challenges for South African producers, having a look at the potential impact on trade with the Green Deal. And also, we asked him to give a few examples of where he sees trouble looming quite soon with lack of control options for certain crop pest matrices. Other point I took away from Cobus is the huge pressure that NGOs around the world are bringing on regulators and policymakers. So that's something we need to continue to be aware of. And when we talk regulators, it's not just the primary regulators, but also secondary regulators such as supermarkets. So Wandile was the facilitator of our first session, and I think he did a great job of getting some interesting discussions going. We took away from that a multifaceted approach is going to be required. We can't just chat to the EU. We've got to come with all sorts of different stories and approaches. Singles approach will not work. Laurie mentioned it a few times, and I believe it's something really key that we have to take back to regulators and policymakers, and that is we need to be very careful that a so-called good policy in one part of the world is not a detrimental policy in another part of the world. So for me, that's something key that we need to take to the decision makers. Session 2 was entitled, Are You a Responsible Registration Holder? And Henk started the session with his thought-provoking, insightful and high-flying presentation. Thank you, Henk. As a long-time supporter of CropLife South Africa, Henk made the excellent point that to really get this industry association going, we need a lot more participation on our members. So thanks for getting that in, Henk. It really was a good punt for the industry. And you also pointed out that the reason that it's worth doing is that all of the initiatives that the industry association do are for the benefit of the whole industry, not just for certain parts. So thank you again for that. Fani then kindly addressed us with the voice of the farmer, if I can call it that, or voice of the customer, to use some of the corporate jargon. And he gave us some of his insights as an export farmer. He outlined the many hurdles that are facing export farmers. And he also gave us good information about the size of the citrus industry. He did pose a pretty good question at the beginning of his presentation, as who is actually the registration holder. So I think that's going to help Alreza and the rest of the team and the marketing committee of Exco. We can start looking at our communications out there. So if a pretty important export farmer doesn't know who owns the registration, we are not getting a good communication out there. Almay then provided some comments about the goals of a certification organisation and confirmed that standards are continuously being raised by these certification bodies. And a lot of that is as a result of demand from regulators but also consumers. Gerard gave the great overview that stewardship and compliance run parallel. Compliance is the big stick and stewardship is the right thing to do. That is your ethical part of doing it. I was very pleased to hear Gerard saying when he speaks to these multitudes of farmers these days that there does seem to be a shift towards the more ethical part of stewardship rather than the big stick part. So thanks for sharing that with us, Gerard. After lunch, we moved into the IPM session. Andrew got that going with an overview of the history of IPM, today's principles of IPM, and introduced a concept which was new to me of the agroecological crop protection. So thank you for that one, Andrew. I'm going to have to go do some homework. We then had the leads of our three main resistance action committees, giving a brief overview of what they're doing. And I was particularly concerned with Cullen's comment that he sees HRAC focusing down on the people who are making recommendations of our products to the farmers. Now, the reason I'm particularly concerned is those of you who do dial into our various RAC meetings, we get virtually zero support or participation from our crop advisors at those RACs. And I think that's something we're going to have to focus on and change. If the people making the recommendations are not participating regularly in the RACs, we're not going to make too much progress. Nicholas then shared with the conference his thoughts on how plant biotechnology can fit into the IPM strategies, which was really quite interesting because I am seriously not the biotech expert. That's why we have Chantel with us. And then we've just had a very thorough overview from Sean as to how IPM toolbox with biologicals can be considered going forward. So I would just like to sincerely thank all attendees today, whether you're here in the room or virtually, all the presenters and all the facilitators for keeping us mostly on track today, and of course to Brand Republic for running such a great session. Reminder, we start again tomorrow at 8:30. We kick off at 8:30, so if you're coming in here personally, please get here on time for tea, coffee. And we're looking forward for a great second day of our conference. I'm going to steal another 30 seconds. Those of you who are planning to come to the AGM on Thursday and you have not yet responded, please do so that we can make sure we have a quorum. And if you can't come and you would like your company's voice heard, please get the proxy forms into either Nadia or myself by close of business tomorrow. So thank you all for your participation. Drive carefully and look forward to seeing you all tomorrow. Thank you.